Let's say you have a function f of x is equal to x squared plus 2x plus 5. Graph it on your calculator and you notice that it never crosses the x-axis. However, it is a second-degree polynomial. It's a quadratic, so it has two solutions. But whenever you do the quadratic formula, you actually discover that both of these solutions are imaginary. They are imaginary solutions. So they are numbers that you could plug into here, imaginary numbers that would give you 0, but they do not cross the x-axis. And that's what we're going to talk about in this video, is how to find the zeros that are imaginary of polynomials that have degrees larger than 2. Okay, let's talk a little bit about complex numbers. Complex numbers include both real numbers and imaginary numbers. And so essentially every single number that exists is a complex number. If it has an I in it, then it's going to be an imaginary. It's going to be in this category. If it doesn't have an I, it's going to be a real number. But both of these are complex numbers. So anytime we ask how many complex roots does a function have, you will list all the roots. You'll list the degree. So if it's a fourth degree, we'll have 4 complex roots. And then we may ask you to break it down and say, well, how many real, how many imaginary? And at that time, you'll list how many. So here's a perfect example. Here you have a quartic function, a fourth degree function. It has 2 real solutions. You can see that it is going to be 3, and it's repeated, so that's going to be 2. And it also has 2 imaginary solutions, I and negative I. Hence the reason why it does not cross the x-axis more than once, but it actually touches here, so it counts as an even root. So what we want to do is we want to identify the zeros. Well, the zeros would be any number that would cause this function to be equal to 0. So x equals 3, x equals I, and x equals negative I. Those are all the zeros. Now, x-intercepts, those are only the real roots because that is where it actually crosses or touches the x-axis. So make sure that you are distinguishing between zeros, any number that makes the function 0, and an x-intercept are only the real solutions. Okay, we want to rewrite this from factored form into polynomial form. So let's go ahead and FOIL this out. So that's going to give us x squared minus 6x plus 9. When we FOIL that, and we FOIL this here, we have to remember that I squared is equal to negative 1. So maybe we want to write that over here somewhere. I squared equals negative 1. That is because the square root of negative 1 is equal to I. So let's go ahead and FOIL this out. We're going to end up getting x squared. And notice that the ix and the negative ix are going to cancel, leaving you with negative I squared. But I squared is negative 1, so that's going to be plus 1. And now we're just going to multiply this out. So we have x to the 4th, and then we have x squared. Then we have negative 6x cubed. And then we have negative 6x. Then we have 9x squared. And then we have 9. So we add all that together. Our final answer is going to be x to the 4th plus, actually minus 6x cubed. Then we have a 10x squared. And then we have a minus 6x and a plus 9. Okay, next we're going to talk about the complex conjugate zeros theorem. And this is a very basic and easy theorem. Basically what it says is that all imaginary roots are going to come in pairs. You will never have an odd number of imaginary roots. It is because if a plus bi is a root or a 0, then by definition a minus bi, which is called the conjugate of a plus bi, is also a root. So notice that the conjugate is simply when you change the middle sign from positive to negative or vice versa. So a lot of problems, it will not tell you that the conjugate is a root. You have to assume it, and here is a good example of that. It says write a polynomial function in standard form whose zeros are negative 3, positive 4, 2 minus I, and you, as the student, must also know that even though they don't say it, that 2 plus I is also a root because you cannot have just 2 minus I. It has to be the conjugate as well. So we're going to start by writing this in factored form. So every factor is always going to be x minus the number. All right, x minus the number. And I know that turns into plus 3, but I want to make sure that you understand that it's always x minus because the number minus itself will give you 0. So it's always x minus. And so this is going to be x minus 4. And then the next factor is going to be x minus parentheses 2 minus I. And then the next one is going to be x minus, not plus, parentheses 2 plus I. Now, you're not going to like this, but we're going to have to multiply all of this out. All right, so let's just make this a big plus sign. So we're going to FOIL this first one. It's going to be x squared minus 4x plus 3x, so that's going to be negative x minus 12. Okay, here we're going to distribute the negative in. It's going to give us x minus 2 plus I. And then this one is going to be x minus 2 minus I. And we're going to just leave this out here by itself for just a moment. And we're going to multiply. X times x is x squared. X times negative 2 is negative 2x. X times negative I is negative ix. And then we have negative 2 times x, which is negative 2x. Negative 2 times negative 2 is a positive 4. And then you have negative 2 times a negative I, which is a positive 2i. And then you have I times x, which is ix. And then I times negative 2, which is a negative 2i. And you got to be careful here. I times negative I is negative I squared. But I squared is negative 1. So that means this is going to be a plus 1. All right, let's see what like terms we have. We have x squared minus x minus 12. And then we have x squared. And negative 2x and negative 2x are going to give us a negative 4x. So I'm going to go ahead and cancel some of these out. We've already done that one, already did that one, already did that one. And notice that the negative ix and positive ix cancel. The positive 2i and the negative 2i cancel. Every time you do this, it's going to happen that way because your final answer can't have any i's in it. So therefore, all the terms that have an I must cancel out. And that's going to leave us with plus 5. Whew, we're not done. Now we got to multiply this together. So x squared times x squared is x to the 4th. X squared times negative 4x is negative 4x cubed. X squared times 5 is 5x squared. And then negative x times x squared is negative x cubed. And negative x times negative 4x is a positive 4x squared. And then a negative x times 5 is a negative 5x. And then we have a negative 12 times x squared, which is a negative 12x squared. Then negative 12 times negative 4x is a positive 48x. This is a long problem. And then a negative 12 times a 5 is a negative 60. So we add all of that up. Our final answer will be down here. So it'll be x to the 4th minus 5x cubed. And then we have a 9x squared and a negative 12. So that's going to be negative 3x squared. 48 minus 5 is 43x minus 60. And there you have it. That is this polynomial function in standard form. Okay, it says use the graph below to find all the zeros. So we know that there's 5 zeros. We clearly see that there are 3 real solutions. So that means there are 2 imaginary solutions. We know it crosses at 4. We know it crosses at 1. We know it crosses at negative 2. So we can use synthetic division. It doesn't matter which order and which ones we use first. So I'm just going to start with negative 2. And I'm going to use 1, negative 3, negative 5, 5, negative 6, and 8. And we know that we should be getting 0 as a remainder because it clearly crosses at negative 2. So we're going to bring down the 1, multiply, negative 2, add, negative 5, multiply, positive 10, add, 5, multiply, negative 10, add, negative 5, multiply, that's going to be positive 10, add, that's 4, multiply, that's negative 8, 0 is our remainder, so we know we did it right. Now we're going to use not the original coefficients, no, we're going to use the new coefficients, and we're going to use 1. Doesn't matter, we could have used 4, the order doesn't matter. So we're going to bring down the 1. We know it crosses at 1, so that's why I'm using 1. 1 times 1 is 1. Negative 5 and 1 is negative 4. Multiply that as negative 4. Add is 1. 1 times 1 is there. That's negative 4. Multiply is negative 4. Add 0. There we go. We have our other root, and now we're going to use 4. So now we say bring down the 1. 4 times 1 is 4. Add, that's 0. 4 times 0 is 0. 1 plus 0 is 1. 4 times 1 is 4. Add is 0. And we see that we have 3 zeros. Now what's left are the the coefficients of your quadratic equation. X squared plus 1 equals 0. We're going to set this equal to 0 to find our other two roots. So x squared is equal to negative 1. We take the square root of both sides. We get x is equal to plus or minus I, because I is the square root of negative 1. It's plus or minus because you're taking the square root of it, and so therefore you have to basically, the way it works with these imaginary solutions is that all you do is put an I on your answer. So if it was square root of negative 25, it would just simply be plus or minus 5I, and that's basically how it works. All right, this one is a long problem. I'm warning you in advance. And we need to find the remaining zeros. We've got one of them, 1 minus 2i. And then by default, we know that 1 plus 2i is a root because they always come in pairs. So we are going to go ahead and get started. Now we're going to have to use synthetic division with 1 minus 2i. And we notice that we have 4, and then we're missing the cubing terms. So you must put a 0 there. And then 17, and then 14, and then 65. Now the good news about this process is we know for sure that we should get 0. So if you don't, that means you did something wrong. So we're going to bring down the 4. We're going to multiply. We get 4 minus 8i. We're going to add, and we get 4 minus 8i. Now here's the hard part. We're going to have to multiply 1 minus 2i. So maybe I'll do it over here. 1 minus 2i. Times 4 minus 8i. So we're going to FOIL. 1 times 4 is 4, negative 8i, negative 8i, and then negative 2 times negative 8 is a positive 16i squared. But that's going to make it into a negative 16 because I squared is negative 1. So essentially, after all of this, we're going to get negative 12 minus 16i. So we're going to go ahead and put that right here, negative 12 minus 16i. Since we're going to need a little bit more space, I'm going to go ahead and erase this because we're going to need to do this a couple more times. All right, so now we're going to add the real parts together. 17 minus 12 is 5. There is no imaginary part on 17, so you just bring down the negative 16i, and we do it again. So 1 minus 2i times 5 minus 16i. 1 times 5 is 5. Negative 16i. Negative 10i. And positive 32i squared, which is a negative 32. So basically we end up getting negative 27 and then a negative 26i. So we can add the real parts together. It's going to give us a negative 13 minus 26i. And you guessed it, we're going to have to do it one more time. We're going to have to FOIL all of this stuff together. So that's going to give us a 1 minus 2i and a negative 13 minus 26i. So that's going to be negative 13. That's going to be negative 26i. That's going to be a positive 26i. And then that's going to be a positive 52i squared, but that's going to be a negative 52 because I squared is negative 1. Hey, that cancels with that. I'm left with negative 65, which is what we said we should get, and we get 0 as a remainder. So we are done with that part, but we still have to use the other root that we know, and that's 1 plus 2i. So now you're not going to like this. We have to do it again. But there is hope for you because this one is always going to be quicker. Watch how quick it is. Bring down the 4. 4 times 1 is 4 minus 8i. Oh, look at that. Plus 8i. The 8i, negative 8i cancel, and 4 plus 4 gives you 8. And then we have 8 times 1, which is 8. And 8 times 2i is positive 16i. Hey, that's going to cancel, leaving you with 13. Then you have 13 times 1, which is 13. And 13 times 2i is positive 26i. Hey, that cancels and that cancels, leaving you with 0. And these become the coefficients of your last two roots. So that's going to be 4x squared plus 8x plus 13 equals 0. You're really not going to like me now because we have to use the quadratic formula. Hey, this doesn't factor. So negative b plus or minus the square root of b squared minus 4ac over 2a. Let's plug and chug. Negative 8 plus or minus the square root of b squared, which is 64, minus 4a, which is 4, and c, which is 13. All of that over 2a, which is 8. All right, let's see what we get. So when we multiply all of that inside, we get negative 8 plus or minus the square root of negative 144 over 8. And of course we know the square root of 144 is 12, but it's negative, so it's going to be a 12i over 8. Hey, I can divide 8 into both of those. So that's going to give me negative 8 over 8, which is negative 1, plus or minus 12 over 8, which is going to be, you can divide both of those by 4, so that's going to be 3 over 2i. And those are our last two roots. Our first two are 1 minus 2i and 1 plus 2i. Last problem here, we want to use synthetic division to factor this all the way down and write it in linear factorization, which is basically factored form. So we need to figure out which numbers we're going to try our synthetic division with. We don't have a graph, so we're going to use the rational roots theorem. We're going to put plus or minus all the factors of 12. So that's 1, 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. All of that over plus or minus 1, which is the coefficient in front of the x to the fourth. So obviously when you divide each term on the top by each term on the bottom, you simply get the terms that are on the top. Now for the sake of time, I already know in advance that 3 and negative 1 work through trial and error for synthetic division. So I'm just going to go ahead and use those. If you did not know that, which you obviously would not, you would have to do synthetic division several times before you get 0 as a remainder. But I've already done that, and I want to shorten this video, so I found that 3 works. So let's bring down the 1. 3 times 1 is 3. That's going to be 1. 3 times 1 is 3. That's going to add up to 4. 3 times 4 is 12. 12 minus 8 is 4. 3 times 4 is 12, excuse me. 12 and negative 12 is 0. And then I know that negative 1 works. Once again, a lot of times the opposite of this second term, second number works when you get it down to a cubing function, but not all the time, but oftentimes. So we're going to bring down the 1, and negative 1 and 1 is negative 1. Add that is 0. 0 times anything is 0. Add that is 4. Negative 1 and 4 is negative 4. That's going to be 0. So we get a second remainder. So our quadratic equation is x squared, that should be a 0, plus 4 equals 0. So x squared is equal to negative 4. X is equal to the square root of negative 4, which is plus or minus 2i. And so our roots are, if we wanted to list them out, it would be x equals negative 1, x equals 3. x equals 2i and x equals negative 2i. But they want us to write it in linear factorization. All right, so that's going to be x plus 1, x minus 3, and then we have x plus 2i and x minus 2i. And that is our function written out in factored form.